Another problem with cards. You draw 2 cards from a deck, and the keyword is without replacement. Find the probability of drawing a 9 from a deck of cards. That's your event A. And event B is also drawing a 9 from a deck of cards. Well, if we just look at what's the probability of drawing a 9 from a deck of cards, which is the probability of just event B, well, there's 4 cards that are 9s in a deck, 1 in each suit, out of a total of 52 cards. The same thing, the event A is the same, so it would be exactly the same. There are, drawing a 9 from a deck of cards, there are 4 9s in a deck out of a total of 52 cards. What you would notice, however, though, is if you started doing the given that's, the little slashes, the conditional probabilities. These are both saying what's the probability of drawing a 9, assuming that you already drew a 9. And the key here is this first little statement in red, without replacement. So assume that you had a standard deck of 52 cards. You pulled out a 9. So that has been done. You pulled out a 9. Now, what are your chances of now drawing another 9? Well, there were 4 9s. We pulled one out. Now there's only 3. And there were 52 cards, but because it's without replacement, there are now only 51. So your chances of, after you draw a 9, drawing another one are only 3 out of 51. And the key here is these probabilities are not the same as this because the conditions changed. Why? Because it was without replacement. Once you pull a card out of the deck, you have changed the conditions because you are not replacing it. You don't have 52 cards anymore. At the very least, now you have 51. So this is what we would call is that these events are going to be dependent because once you pull out a card, you are not replacing it. The probabilities don't stay the same. They will change. So that's what it means for something to be dependent. Do your probabilities change once something has happened? And it will never stay the same if you are not replacing whatever it is. Now, however, it would be considered independent if we put the card back. Why? Because the probabilities wouldn't change. You would still have all 52 cards and all 4 9s to choose from. So the probability would stay the same. The only reason why the probabilities changed was because we pulled out the card and we weren't allowed to put it back. So we didn't have the 4 9s anymore. We only had 3. And we didn't have the 52 cards anymore. We only had 51. So that's kind of the idea between independent and dependent. Have you changed your conditions? And this is going to be really important to read your problems carefully. Okay, our last rule is going to have to deal with, instead of ors, we're going to look at ands. And what the probability rule for and say, and this will work for multiple things that you're looking for, not just what's the probability of choosing this and this. Let's say rolling a 1 and a 2 on 2 different dice. This would be if I wanted to do, let's say, 5 dice or 5 cards or something fancy, or selecting 2 or 3 or even 5 people from a group. So what the probability rule for and says is, now with ands we want to get used to, now and is going to mean that we're going to multiply. So we're going to think of ands as multiplication, where we thought of ors as addition. And what the multiplication rule says is find the probability of your first thing first, which in this case I'm just calling A. So I'd find the probability of that first, probability of A. And again, the and means that we're going to multiply. And then you want to find the probability of your second group, B, and multiply by that. But going to be careful how I write this. I'm going to do a slash with an A. We have to assume that A has already happened, whether it affects anything or not. Then if there were more things, we would assume A and B have both happened. Now what's the probability of C? And keep multiplying your probabilities as you go along. But each time you add another and, you have to assume that the ones before it have happened. So your conditions may be changing. May. They don't have to if they are independent. For example, with cards, if you keep sticking them back, you're not into the deck, you're not changing anything. But if you're keeping them out each time, then you are changing your conditions with each new event that happens after that. And each and is going to tell me I'm going to be multiplying a new thing, which may mean we get some really big numbers on our fractions, and that's okay. If 3 of the 100 subjects are randomly selected, find the probability that they are all group B and RH negative. So notice we have, let's see, when we're looking at B, type B blood, that are also type RH negative. If you look at the overlap there's a total of 5. There's a total of 5 people that have B negative blood. The problem is, if you look at part A, they say that we're going to select these 3 people without replacement. That is very subtle, but very, very important that they're saying without replacement. So we've got 3 people that we're selecting. So we're going to be finding the probability here. So let's start out with a P for probability. That we've got the first person needs to have B negative blood. The second person needs to have B negative blood. And let's see, the third person needs to be B negative blood. And the question is, what connecting word goes in between all 3 of these, which is the word and. So let's see. For the first person, we're going to go one at a time. For the first person to have B negative blood, let's see. The first person to have B negative blood, well, there were 5 out of the total, which they said that there were 100 subjects. That's your probability for your first person. Now, remember how this works with the ands is now we have to assume that that person was selected and pulled out of the group without replacement, and now move on to your second person. So there were 5. Now we're down to only 4 out of, instead of 100 people, now we're down to 99 for our second person to have B negative blood. Okay, now that person has also been selected without replacement and is out of our group. Now let's talk about the probability that the third person will now have B negative blood. Well, there were 5, then there were 4. Now there's only 3 people left with B negative blood. There were 100 total, then 99. Now we're down to a total of 98 people. Now the question is, what do we do with all these fractions? Well, this word and in between, that we want all of these things to happen between our people. It's not an or. We want all of these things to happen. That's why it's an and. Remember, the and means that we're going to be multiplying these probabilities. So the question then becomes, how do you multiply fractions? And remember that you multiply fractions by going straight across the top. The 5 times 4 times 3, which is 5 times 4 is 20 times 3 is 60. Then the big hard part is actually going to be multiplying out the denominator, which is the 100 times 99 times 98. But let's figure out what that is. We've got 100 times 99 times 98, and that's going to be a total of 970,200. Now remember, we don't want to leave our probability, and this is our probability, like a fraction like this. We want to leave it as a decimal if we can. Now, my calculator went ahead and turned it into 0.00006 and then a 2. Your calculator might have done something like this instead. which is 6.2, and then a bunch of other numbers, and then an E, and 1, 2, 3, 4, and probably put a -5 at the end. If it did do that, what it's done is actually put the same answer I got, which is your final answer, but it might have put it in this form, which is scientific notation. The 6.2 is what goes out in front, the times 10 to the, and then there's the exponent, the -5, which is the same thing as this value, the answer that I got from my calculator. Remember, the -5 tells you that you need to move your decimal place 5 places to the left, which would mean that you jump your number 6, that's your first place, then you jump 1, 2, 3, 4 more for a total of 5, 3, 4, 5 places, which means you'd have to fill in these blank 4 spots with missing zeros, with zeros as your kind of your placeholders, which does give you the 0.000062 that I got before. So you do actually get the same exact answer. It just may be displayed, depending on your calculator, a little bit differently. Let's take a look at one more. What happens if we look at the same exact problem, but this time we actually look at it with replacement? That actually does change the problem quite a bit, because we'll still have the probability of the first person having B negative and the second person having B negative blood and the third person having B negative blood, and I don't want to get confused here, so let's kind of quarter that off. But here's the difference. If we're replacing, the probability of the first person having B negative blood was just 5 out of 100. But now, if we replace that person back into our group, the probability of the second person also having B negative blood is still another 5 out of 100, because we didn't take that person out. We replaced them. And the probability for the third person having B negative blood is also another 5 out of 100, which, let's see, then again, remember, just like before, the ands would be telling us to multiply these 3 fractions. So straight across the top, we'd be multiplying the 5 times 5 times 5, which is 125. And on across the bottom, we'd be doing the 100 times 100 times 100, which is 1,000,000. Which the question is, what is that as a decimal? As a decimal is 0.000125. Another way to do this same problem, because your probabilities do not change, would be that you could just redo this as 5 over 100 and then raise to the third power, because they're all the same. And what you would notice is you'd get the exact same answer, the 0.000125. And it doesn't matter on a test which way you do it. But the only way you can keep it as that it's raised to the third power is if it is with replacement, because then your number stays the same each time.